Today on How It's Made. LED tubes. We shed some light on these dainty diodes. It's illuminating. Chocolate peanut butter bars. Wrap your mouth around this nutty feature. It's sweet. And robotic medication dispensers. Machines are taking over the world. And here's how, one chemist at a time. But first, LED tubes are designed to replace standard fluorescent tubes inside overhead commercial light fixtures. Unlike traditional incandescent and fluorescent lighting, a light-emitting diode produces light through a microchip. It lasts twice as long and uses less than half the electricity, which is a bright idea. These LED tubes come in various lengths. They're designed as a modern, energy-saving alternative to use in those ubiquitous overhead fluorescent tube light fixtures found in offices, shops, hospitals, and schools. The process begins with a printed circuit board. Printed means the board has a network of conductive copper lines and rectangular pads, designed to electrically link electronic components together. A technician places the circuit board on a track, which ferries it to the first computer-guided machine on the line. The machine covers the board with a metal stencil that has openings matching the locations where the electronic components will be mounted on the board. Then the machine spreads a layer of lead-free tin alloy solder over the stencil. This only applies solder to the board where the components will go. The next computer-guided machine on the line mounts the first of those components, the light-emitting diodes, or LEDs. They're composed of a microchip coated with the chemical phosphor and come in different sizes, colors, and light outputs. The factory programs the machine's chip shooter to pick the required LEDs off supply reels and place them on the solder-coated locations on the circuit board. The chip shooter works at astonishing speed, placing up to 11 LEDs a second. It places each one with absolute precision. But just to make sure, a camera focused on the board verifies that every LED is in exactly the correct position. The circuit board now moves to a third computer-guided machine for the next electronic components, the terminals. The terminals receive the electric current to power the LED light tube. The machine picks one terminal at a time and places it at one end of the circuit board. The circuit board then moves to the final machine on this line, a tunnel oven. The temperature inside peaks at 240 degrees Celsius. The heat melts the solder, fusing the components to the board. Solder is both adhesive and conductive, so this bond also connects the components to the board's copper electrical network. For the high light output tube they're making here, each board is comprised of 8 strips, each of which has dual rows of LEDs. The strips are snapped apart. Each one is 30 centimeters long. The tube length being made requires 4 strips. On the assembly line, 1 strip with the terminal and 3 without are slid into an aluminium track. The technician gives them a thorough visual inspection and then solders the strips to each other. Once soldered, the strips are electrically bridged, so the terminal on the first strip can power all of them. The aluminium track, called a heatsink, is critical to the tube's performance. It has deep fins on the bottom, which dissipate heat, cooling the LEDs. This keeps the color of the light consistent and extends the tube's life. Once the technician has connected the strips, he plugs a power source into the terminal to test the LEDs. Next, he inserts wires into the terminal and locks them in with a compression tool. The opposite ends of the wires connect to the power supply in the light fixture. A transparent polycarbonate lens is snapped into the grooves on the side of the heatsink. The tube is closed up by placing a cap on each end. Each cap's pins are aligned with slots on the press. The press is then activated, which forces the caps into the tube attaching them permanently. The end with the terminal has slots in it, enabling the wires to protrude. The light tube is finished and ready to be boxed for shipping. To install this energy-efficient LED tube, you simply click the pins on the end caps into receiving slots in the light fixture. Then connect the wires to the power supply and the fixture's wiring. Thanks to the cooling fins on the heatsink, one LED tube lasts for 100,000 hours and has a guaranteed 10-year lifespan. So for this light, you could say the future's bright. Right, time to indulge my sweet tooth. And, as any chocoholic can attest, there's no end to the flavours you can pair with chocolate. A long-time favourite combination is milk chocolate and peanuts. The savoury contrast of peanuts is the perfect foil to the sweetness of the chocolate. Nice. This bar features a thick layer of milk chocolate around a sweet, salty and crunchy peanut butter candy centre. But making that peanut butter candy centre is the tricky part. The process begins by combining liquid sugar, corn syrup, coconut oil and molasses. They mix and heat these ingredients for 8 minutes. They then pour the cooked candy into a large bowl. Next, they add the leftovers that didn't get used in the previous production run of candy chocolate bars. They call these leftovers rework because they rework them into this new batch. Once the rework has softened up and been mixed in with the hot new candy, they empty the bowl onto a cold stainless steel table. They blend the candy until the rework gradually melts and the two merge into one sweet, gooey mass. Once the candy has cooled slightly, it's folded up and carried over to the pulling station. Here, they make a pocket in the centre and fill it with vanilla extract. It's then time for the pulling machine to do its thing. The machine repeatedly stretches the candy non-stop for 5 minutes. This infuses the candy with air so that its consistency is soft rather than hard. They then transfer the candy to a belt that transports it to the weaving machine, which will weave in the peanut butter. The machine's roller first flattens the candy into a thin sheet. Then a pump draws piping hot peanut butter from this tank and deposits it in a layer onto the candy sheet. The sheet is then rolled up. When the roll reaches a specific diameter, they fold it and place it on a blank sheet, meaning a sheet without peanut butter on it. The next roller presses the folded roll flat onto the blank sheet. Then they roll up the blank sheet, sealing the peanut butter candy inside. This complex assembly is what forms the flaky layers in the chocolate bar centre. The whole mixture is then rounded out between two rollers and fed to the rope sizer, a machine that stretches the peanut butter candy into a rope so that it's the exact diameter of the centre of the chocolate bar. The next machine makes a pinch mark every 12.5 centimetres, the length of the chocolate bar. The link centres then enter a cooling tunnel set to 7 degrees Celsius, and they exit 5 minutes later, rigid. As they drop to the next conveyor belt, they separate. They then pass through a second refrigerated tunnel, which finishes cooling them. The centres move into lanes that feed the enrober, the machine that will coat them with chocolate. Eagle-eyed watchers make sure that the centres proceed in single file and are properly spaced. The centres pass through a hot rinse of milk chocolate. Then, an overhead dryer blows off the excess, leaving a layer of chocolate that's consistently 3 millimeters thick. The bars enter a final cooling tunnel to harden the chocolate. The finished chocolate peanut butter bars are transferred to a conveyor belt that lines them up for packaging. As the bars approach the wrapping machine, the in-feeder arranges them in single file. Rolls of printed plastic film unwind into the machine's forming box, which quickly folds, wraps, and heat seals the film around each passing bar. A revolving knife slices the wrapper between the bars. It's then off to the packaging department, where they're packed 24 to a box. And now these bad boys look good enough to eat. The question is, why are there only 24 in a box? Mind you, I could just get another box. Coming up, we enter the world of automation with robotic medication dispensers. These medical marvels not only select the correct medicine for you, but they can count out your pills, put on a label, and deliver them to you too. See you after the break. Welcome back. Now you may have caught a glimpse of these beasts on your last trip to the chemist's, lending a hand behind the counter. These machines can count pills, dispense them into vials, cap the vials, and even label them. So, when it comes to handling a heavy workload, these robotic dispensers are just what the doctor ordered. Input the prescription data, and the robotic helper in this dispenser machine goes to work. It counts, bottles and labels pills in just 35 seconds, a fraction of the time it would take a human to do it. Making one starts with the retainer disc for the vial capping system. Computerized tools carve slots for the capping mechanisms. With an electronic probe, they measure the slots. More tools sculpt a rough plastic blank, transforming it into a platform for the pill vial during capping. The part takes shape in just minutes. A technician now installs 2 computers in the dispenser frame. One computer will interface with the robotic system. The other will operate the drug inventory. A rack that holds a power strip above the computers is then installed. And a battery is lowered into place beside the computers and attached to the frame. This battery will provide power backup in the event of a power cut. Next, the controls for the robotic arm are incorporated. They're inserted into the frame and plugged in. Another member of the team assembles plastic brackets to an aluminium manifold. These brackets will hold cells filled with pills. The manifold will send dispensing information to the cells. It will also deliver bursts of air to move the pills through them and into the prescription vials. The brackets are now fixed to the manifold securely with screws. A long row of circuit boards is then attached to the manifold. These circuit boards will send data between the cells and the dispensing computer. A ribbon cable is connected to the computer board circuitry. This cable will be linked to 18 other manifolds in the dispensing machine. They're now ready to mount all the manifolds to a large metal frame. A technician slides the ends of each manifold into slots in the rack. She stacks up the cell manifolds, creating a bank of 18. She then attaches plastic dividers to the brackets. This creates compartments to hold the actual pill cells. The dividers also strengthen the entire dispensing machine structure. Another technician now installs a vertical rail that's equipped with the robotic arm. He fits the bottom of the rail into the grooves of a horizontal track and attaches the top of the rail to an upper track. Then, he connects one end of a long pole called a link shaft to the robot and the other end to the top track. This shaft moves the robotic arm horizontally to collect pills in a vial as needed. Once installed, the shaft is tested to confirm that it moves the arm along the track with no obstructions. The robotic arm is then programmed to zip up, down and around in order to collect the pills during dispensing. Rubber flaps are attached to the back of all the pill compartments. They'll absorb the sound of the equipment to keep the noise level down. Full tanks of compressed air are fitted to the grid. The compressed air will be pumped through the manifolds to move the pills through the cells. A technician now assembles the exception carousel. It'll capture tablets that haven't been perfectly dispensed, vials that have too many or too few pills in them, or haven't been correctly labelled or capped. He inserts the motor assembly in the centre cavity and snaps the top into place. A metal framework is then screwed to the assembly, and the technician confirms that it spins freely within its housing. He then scans the serial number for tracking purposes. 80 man-hours goes into making each machine. It's a long and complicated process. The robotic dispenser is nearly complete. The next step is for a technician to mount the newly assembled carousel into the centre of the machine. He attaches the touchscreen controls above the carousel, and he wires all the operations to it. It's now time to assemble the labelling system for the pill vials. The first component is the device that spins the vials as the labels are applied. It's wired to a motor and then placed in the housing. A sensor that will detect the presence of a vial is connected. The technician then attaches the printer to a computer circuit board and then tucks the printer into the housing. It's now time to test the unit. A vial is loaded and the labeller takes it for a spin. The system unwinds the paper and prints the prescription information on it. Then, small protruding rubber arms wrap the sticky label around the spinning vial. Once the unit has met company standards, it's installed in the medication dispenser. It's positioned at the bottom at the front of the machine's base. 2 vial storage units are then mounted above the labeller. One is for smaller vials and the other is for larger ones. There are mechanical levers inside each unit for holding vials until they're needed for labelling and filling. When called upon, they'll ride these plastic chutes to the printer. The capper that twists the tops onto the vials is installed beside the vial storage and delivery system. These are the drop-off bins, where the completed prescriptions end up. Another technician encases the control screen and the carousel below it with a plastic frame. This trims and finishes these components. He fits an emergency stop button to the switch above the control screen. To protect the sensitive electronics, they encase the entire machine in a sturdy plastic cabinet surround. Now, the finished machine has to be calibrated so that it knows what tablets it's dispensing and where. He programs the number of pills to be counted and the amount of air pressure that will be needed to propel them through the throat of the cell, where sensors do the actual counting. After each pill cell has been programmed, a technician clicks it into place in its slot at the back of the dispenser. There are up to 228 of these cells, and they'll hold the most commonly dispensed medications at the pharmacy. Each cell has been programmed to dispense a particular pill. He now scans the barcodes on each cell to log the pill inventory. The barcode is the serial number for the cell. This robotic medication dispenser is now ready to be put to the test. Pill vials are loaded into the storage compartments at the front, and caps are placed into the compartment beside the vials. Then, moving around to the back, pills are loaded into some of the cells. For the purpose of this test, the pills are plastic copies. Sensors in the cells automatically count the pills that are loaded. Then, the technician inputs the test prescription. A vial drops and the printer labels it. The robotic arm then takes the vial to the correct cell, where it rotates and slides sideways to deliver the pill vial to the capping operation. A second robotic arm then presses and twists the cap onto the vial. And the prescription is now filled. From labeling to dispensing to capping, this process has taken just a few seconds. And in your local chemist, this robotic medication dispenser should prove to be, well, indispensable. I wonder if it'll dispense a spoonful of sugar though.